Oh, all right, good morning. I am finally back in the saddle with the reading group, and I'm going to do my customary double checking to make sure that everything is working. So it looks like Encoder is receiving, and Twitch is working, and YouTube is working. Good morning, everybody. And I'm going to pause these so I don't have playback issues, which I did, I think, on Friday afternoon. I had some playback issues, so keep an eye on that and make sure that we don't have like weird stuttering and stuff. So attention is all you need. Last time, like a month and a half ago, before I got really sick, and then we had the dashboarding event, and then it was the holidays, and I mean, it's still the holidays, but I am back in the office today. To be clear, I am not working while I'm on vacation. I have not taken today off. We are back in the saddle with this paper. So last month, basically, we got all the way to page 3, and we had just finished the attention section. And the video for that is going to be on the Kaggle YouTube channel, which is, if you're on YouTube where you're watching this, under the playlist Kaggle Reading Group. And I'll make sure to add this video as well once it is done uploading. And the things that we've gotten so far is we'd pretty much gotten most of what is discussed in this particular diagram. That's what that's called. Oh my gosh. Nakaduke says, glad to hear you're feeling better. Thank you. I am much happier to be feeling better. It was a rough one. I completely lost my voice for 4 days. Like, I've never had laryngitis that bad before. Yeah, it was a pity I had to miss a workshop. But anyway. So the sort of general idea, and this is sequence to sequence, right? Yeah, except they call it something else. They call it like sequence transduction. Sequence transduction. So we are not taking in, let's say, a word and putting out, you know, a single thing. Like, we're not doing what's the word I'm looking for? We're not doing something like sentiment, right? Where you have your input, you know, strings, and then out you get a single value. We're taking in a string and then putting out a string. So transformers, which is what this type of model is called, has had a lot of success with like machine translation in particular. Inari on Twitch says, hey, love the concept. Always wanted to see people stream reading papers. I'm glad I can provide content that is interesting. When I first proposed this, some people were like, that sounds so boring, Rachel. And I was like, maybe it will be, but it's better to read papers with friends, I always say. And Nekaduk on YouTube says, sorry about the misspelling. No worries. It does not bother me. I'm dyslexic, so I usually don't even notice. So the general idea of what we've gone over so far, and this is to refresh my memory as well because it's been like a month, is that you have, so your input embedding layer, rather than having a co-occurrence matrix where the size of your vocabulary is squared, you have a lower dimensional projection. Holy crap. Polar says, you're wrong. This is awesome. Oh, I'm glad you think so. So that's pretty standard in most NLP applications these days. And I think actually Kaggle has a course about it that launched relatively recently that's a little bit more hands-on that Colin Morris put together, who also has a background in NLP. So if you're interested in learning more about embeddings, you can check that out. And then positional encoding, I don't think we talked about, and we haven't reached that point in the paper. I don't know what it is still. We'll get there. And then this multi-headed attention. So we talked about the attention layer, and what we figured, so they talk about these key value pairs to an output where queries, keys, values, and output are all vectors. And we were using this this illustrated Transformers blog post, which has some really nice visualizations to help out with that. And where I believe we got to last time was that the queries, the keys, and the values are all trained matrices that we are training as we train this particular model. So these aren't... so for me, when you say query and key, I'm thinking like database that's static, but these are things that we are actually updating as we're training our model. I don't love the naming in this paper. Some of the terminology is a little bit confusing. So we have the dot product of these two matrices, and then the values are, once we've done this transformation, an additional term that we multiply by to downweight less relevant words. And after we use this value transformation, that's the point at which I believe it stops being really interpretable. I believe is where we got to last time. So we have this the dot product of these two here. They're vectors, but they're this is done via matrices in the full model, just to like make things a little bit faster. And then the values are what is being represented here, where we are upweighting the word thinking and downweighting the word machines. And this is the score for the word thinking. So that's the self-attention part of it. And then from those, we take the softmax of the queries and keys, and then we multiply by the values, which again is trained, and then finally we take the sum. So this is no longer interpretable. It is at this point, which is the last point where you can sort of get understanding out of it. Let's see, Sonyam on YouTube says, I haven't really read a research paper ever. Is it a wise idea to pick this one as a first read? This paper... I would probably start with some of the papers that this builds on, like some of the RNN papers. I don't know, it's hard to say what's a good first paper. This paper introduces a lot of new concepts to the field. So if you start with this one, you'll have a good understanding of those, but you won't necessarily have a good understanding of like what that's in dialogue with. So shrug. And I will say I would only really recommend this as sort of the first model to tackle if you're really interested in those sequence to sequence type of questions like machine translation, or I don't know, like text-based style transform or something like that. Aziz says, why dividing by 8? And what is the square root of dk? I believe this dividing by 8 dk, let's see. Blah, 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 blah. Weight assigned to each value, scale dot product attention. So that is section 3.2.1, which we haven't read yet. And I'm going to blow my nose really quickly, and then I'll be right back and we'll get started on it. All right, I'm back. Sorry, I just wanted to make sure that I was muted when I blew my nose, so y'all didn't have to hear that. So that scaling is what makes it scaled dot product attention, which is discussed in figure 2. So this is the new stuff that we haven't done yet. The input consists of queries and keys of dimension dk, and values of dimension dv. So this is just the dimension of the input matrix. So here it would be 3, because these are, the query and the key are going to be the same dimensions long, and here it would be 3, and it is 8 here, because that's the square root of 64, which is the dimension that we're actually using in the paper. So this visual representation is too short, and it should be longer if we're showing the same architectures in the paper. I mean, the overall structure is the same. It's just the dimensions that are different. Okay. And the reason that they do this is that it leads to having more stable gradients. So there could be other possible values here, but this is the default. Excuse me. Sorry about that. Okay, so if we didn't have stable gradients, we would potentially get stuck in local minima more often during training. Or we might have, what's that thing where there's like it's like a sort of like a loop shape, and then you overshoot it, and then you overshoot it the other way because your training rate is too large for the minima you're trying to reach. Inari says on Twitch, I'm confused. What are output embeddings? E.g., if the input embedding is word2vec, the output embedding is ? That's a good question. So this is for something. Oh, right. I remember this. I remember talking about this. So this would be for like machine translation, where this would be the input words, and this would be the next word. So what we're doing is we have the model of everything that we've translated so far, and then the current word that we're trying to translate. So we're considering both the things that we've already translated and then also the current word in our input sequence. Exploding gradient, Sanyam says. Yes, thank you. It's the word I was looking for. Yeah, good questions, everybody. Yeah, and I think that these would be the same embedding system. It's just that they are for different words. That's a good question. Okay, I'm gonna sneeze. Oh, excuse me. I don't know why I'm so sniffy this morning. Okay, I might be allergic to something that's blooming. Okay, and then we. Oh my gosh, excuse me. My apologies. Okay, so we take the scaling is that square root of decay that we do, which results in more stable gradients. And then, so that's the dividing each by decay, and apply a softmax function to obtain the weights on the values. So that is this point is the softmax score, and then we multiply it by the values, which upweight the words that we're more interested in, and we downweight the words that we're less interested in, and then we sum across all of those, and then this would be the output that is passed to the simple feed forward attention network. People are saying bless you. Thank you. So sneezy. Actually, I'm gonna go blow my nose again. I'm sorry. Alright, I'm back. I might be developing seasonal allergies. I've been living here for like 6 years now, so I think that's about the time when you might start to find them. Okay. And then, so this is all the encoder. So this is what we take the so the encoder takes in the text that you are interested in, and so like for machine translation this should be like alien language A, and then at the end of that you get a vector that's sometimes called a thought vector, quote unquote. I'm not a huge fan of that terminology, and then that's what you use as the input to your decoder, which takes that thought vector, quote unquote. I'm doing little air quotes, but you can't see them, and then gives you your translated text based on some other inputs. So the parts of this that I don't understand yet are the positional encoding and what makes this masked. All right, let's see. Scale dot product attention. So this is what we looked at over here. So we take our queries and our keys, which are both trained matrices. We take the dot product of those. We scale them using the square root of dk to prevent exploding gradients. And then we mask. I don't know what that is. And then we take the soft mask. And then we multiply that by the values, which we are also training to upweight more important words and downweight less important words. And then that is the output of the dot product attention. It's me says, hey Rachel, I'm learning NLP from the Jason Brownlee book. Is it good enough to help me start building project and text-based data? I'm not actually super familiar with that book, so maybe. Yeah, sorry about that. And Chandrashu says, what is the topic? We are reading the paper, All You Need Is Attention, which is about the transformer model, which is an alternate neural network architecture to long short-term memory, and in particular bidirectional long short-term memory with attention, which for many tasks is still state-of-the-art, and when this paper came out 2 years ago, was sort of the front runner in machine translation as well. Okay, so we talked about that. We call our particular attention scaled dot product attention, figure 2. And then the multi-headed attention, I'm still not entirely sure what it is doing. Linear. So it looks like it's a tensor with the dimension linear. I don't know where they're getting linear from. And then they do scale dot product attention H. I don't know where H is coming from. And then they concat. I don't know if that's the same as the scaling here. Are these colors supposed to be representing things that are parallel and then linear out? So maybe the multi-head attention is just taking these vector operations and applying them as matrix operations across multiple words at the same time. Ryan on Twitch says, I haven't read that book specifically, but he has a ton of different tutorials. It could definitely help you on a project. So that is to It's Me from Ryan Chester on Twitch. And Inori says, I don't think color has meaning between figures. Okay, that's helpful. I probably would not have used color here. I don't know. I don't tend to like encoding a lot of information in color just because it's not very accessible to people who are colorblind. Is tensor a matrix? Was asked on Twitch by Bubble Ride. So a matrix has 2 dimensions. A tensor has more than 2 dimensions, basically. So like a 3-dimensional matrix-like shape would be a tensor. You may be familiar with tensors from things like TensorFlow. Ryan says, the linear units are 3D, and the scale dot product attention is 2D, and then concatenated flattened to 1D. Okay, so the linear units are 3D, so these would be tensors, and then the scale dot product attention is 2D, so at this point we get to a vector, and the H on the side of the diagram is the number of dimensions. Okay, that makes sense. So we're going from tensors to vectors to a scalar. Okay, that was very helpful, Ryan. Thank you. Okay, so the multi-headed attention is the same as the dot product attention, more or less, except happening in more dimensions simultaneously. Yeah, we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as attention given Q, K, and V is the softmax of Q times K to the T power divided by the square root of D sub K, the softmax of all of that, multiplied by V. So Q and K are trained matrices, queries, and keys. T is something, huh? Square root of dk is the scaling, and that is the dimension of k. And then we take the softmax of that and multiply it by the value, which we are also training. And then that is the output of attention. What is T? Where do we get T from? Is it discussed up here? Q times K, T. All right, so here, let's see. Q times K, softmax. I don't think it's represented here. Yeah, I don't know what T is. To the T power. Oh, okay. So this must be the dimension of Q? Oh, Inari says T is transpose. That makes sense. So it's Q times the transpose of K. That makes a lot more sense. Thanks, Henry. It's Me says, how does reading research papers help in writing code for that topic based on maths of that paper? So a research paper for a new type of model is basically a guide to what's happening in the model. So if you just like, if you used open source code for a research paper and you were finding that your model wasn't having good performance and you wanted to change something, if you didn't understand what was going on and what each of the parts of the code was doing, then reading the research paper would help you understand what you could tune, what you shouldn't tune, what you might, do grid search for, that sort of thing. So it helps you build an understanding and an intuition of the model. And depending on, your background and what you're comfortable with, you might prefer to build that intuition from just looking at the code. But my personal experience is that I find a combination of looking at the code and the paper to be most helpful in understanding what's actually going on in a model. Yeah, I'm going to blow my nose again. I'm sorry. I'm back. I'm beginning to suspect I might have like a mold allergy, maybe? I don't know. It's very rainy here in Seattle, to no one's surprise. Okay. Dot product attention is identical to our algorithm, except for the scaling factor of 1 over the square root of dk. So here it would be times 1/8 because the dimension of k is 64. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. So this would be the approach that had been used previously for things like, there we go. For things like bidirectional LSTMs with attention applications. I think I mentioned this last time. This paper didn't propose the idea of attention. It just proposed a model that uses attention in terms of things like in opposition to things like recurrent structure. While the two are similar in theoretical complexity, I almost said complexability, not a word, dot product attention is much faster and more space efficient in practice since it can be implemented using highly optimized matrix multiplication code. So the problem with a feed-forward network in attention is that you need to compute every previous layer before you can compute every previous, item in the sequence before you can compute the current sequence. And this can compute all items in the sequence simultaneously, so you get a speed increase. Okay, well, for small values of dk, the two mechanisms perform similarly because this term is going to be closer to 1. Additive attention outperforms dot product attention without scaling for larger values of dk. 3, and that is a citation, and it is a citation to somewhere at the end of the paper. Denny Britz, Annie Goldie, Ming Tang Luang, and Kwok-Fi Lee, Massive Exploration of Neural Machine Translation Architectures from Core, which is that paper I don't really, that venue I don't really know a lot about. I'm just going to take their word for it. Blah, blah, blah. We suspect that for large values of dk, the dot products grow large in magnitude, pushing the softmax function into regions where it has extremely small gradients. So it would take a really long time to learn, or you'd need a very large learning rate. To counteract this effect, we scaled the dot products by 1 over square root of dk. Okay, so that's what they mean when they say more stable gradients. JRC Fernandez on Twitch says, can you show the name of this article? Yes, this article is called Attention is All You Need. It was from NeurIPS 2017. So not the most recent one, but the one prior to that. And it is the paper that proposes transformers as a model architecture. It's Me says, does working as a data scientist need to have implementation of a new model in production development? Let's say about attention model. Is this too new to implement in production? I would say it would be very dependent on your particular project. I would probably only use this for sequence to sequence. I don't think attention has had good results in things like text segmentation or labeling. Yeah, it depends. I mean, I know a lot of people just sort of try a bunch of different things and then figure out what works best for their particular application. Bubble Ride says, is this a similarity matrix? Similarity metric? Attention kind of is. But it's more a metric of what's important for the task at hand. Broadly. And then Tech says, how to train my data if it is on visual data like video. Not using this. This is a text model for NLP, so you would probably want a whole different class of models for video. Excuse me. Okay. So that is the dot product attention. The multi-head attention, which is this bit and happens in the first layer in the input embedding, and then happens twice in the, so this would be the encoder and this would be the decoder. So it happens once in the encoder, twice in the decoder. Instead of performing a single attention function with D-model dimensional keys, values, and queries, so having I think it's 64 in the paper that they've talked about so far, we found it beneficial to linearly project the query's keys and values H times with different learned linear projections to DK, DK, and DV dimensions respectively. On each of these projected versions of queries, keys, and values, we then perform the attention function in parallel, yielding DV dimensional output values. These are concatenated and once again projected, resulting in the final values as depicted in figure 2. So that's what I was mentioning before, where you can look at the whole sequence simultaneously instead of having to look at each step in the sequence. Multi-headed attention allows the model to jointly attend to information from different representation subspaces at different points. With a single attention head, averaging inhibits this. So you can be working on training multiple matrices for queries, keys, and values simultaneously, and because you have sort of like a lot of irons in the fire at the same time, you can be tweaking them each individually, rather than if you're looking at a composite of all of those things, you have a hard time, changing. All right. And then this is a footnote about why the dot product gets large. So this discussion of for large values of dk, we get very small gradients. Assume the components of q and k are independent random variables with mean 0 and variance 1. Then their dot product of q and k is the sum of from dk to I equals 1 of q sub I and k sub I has mean 0 and variance dk. Okay, so what this is saying is that even if the variance of q and k are both very small, when you take the dot product, the variance becomes very large. So dk here is 64. So even if you started out with relatively small variance, you're going to end up with very high variance, and that means that your gradients are going to be very shallow. If you can imagine like a normal distribution with a mean of 0 and a variation of 1, most of your data is going to be within 4 points on your scale from your mean of 0. If your variance is 64, most of your points are going to be within whatever 128 times 2 is 256 points on your scale. So it's a much shallower curve. It's me says internship position all time for Kaggle or data science or analyst. So Kaggle is part of Google. So to do a Kaggle internship, you would have to go through the Google internship application process and then be matched with Kaggle. So it's a whole big thing, and I would look at the Google site for that. All right, so that is the footnote. And then here are the formulas for multi-headed attention that I'm not going to read aloud because they are the same thing here, and I think we've talked about them enough. Unless folks aren't following. Where projections are parameter matrices, matrix Q of the query is going to be the, oh my god, we talked about this last time and I have already forgotten what it was, but it's going to be the dimensions of the model times the dimension k, which is here the dimension of the keys, and then the same thing for the keys. They're going to be the dimension of the model times the dimension of the keys, because the keys and the queries have the same dimensionality. And then for the values, they're going to be the dimensions of the model times the dimensions of the values. And O, which is... I don't know what O is. I don't know where O is coming from. Is going to be H. Oh, so this, so the number of things that we're looking at simultaneously here. H times the dimension of the values times the dimension of the models. Inari says output. O equals output. Yeah, I think that's probably right. Bubble Ride says how to code this in R. That is a good question. I don't know. I would have to do some digging. I'm pretty sure that the code for this paper is in Python. Yeah, I don't know. Maybe that's what I'll do on Friday. And then Bubble Ride on YouTube also says O equals output. Yeah, I think so. Thank you. That was helpful. And this is the sort of this is the things that make me frustrated about math papers sometimes. There's like, of course O is output. And you know that if you know that O equals output. But if you don't know that and you don't have that training, you just don't know about it. All right, in this work, we employ H equals 8 parallel attention layers, or heads. So that's this value here. So we're training 8 separate matrices for our values, matrices for our keys, and matrices for our queries at the same time. For each of these, we use dk equals dv equals d model divided by h equals 64. So we have 64. So our keys are 64 by 64. Our values are 64 by 64. Our model is 8 because the dimensions of our model are 64 divided by h is 8. No, so this would be 8 times 64. And then that would be 64. Okay. Due to the reduced dimension of each head, the total computational cost is similar to that of single-headed attention with full dimensionality. Oh, I see. So each of these layers here in the scale dot product attention is smaller. So we're training a lot of small models simultaneously instead of one big model all the way up. Bubble Ride says, a notation table should be obligatory. Yeah, that'd be nice. And then Inari says, how to code it in R, code it in Python, and then call from R with the reticulate package. Yeah, potentially. Well, I mean, we have, R has a Keras wrapper that is, you know, pretty good, so I think it's doable. But I need to make sure that I understand the model first so I can make sure that I am doing the things that I think that I am doing. All right. So we were talking about why this is faster, is because you have several small models that you're tuning, so you have fewer things to change as opposed to one big model. And then Doa says, does Kaggle open all time? Does internship open at all time at Kaggle for data science? I mentioned this a little bit earlier. It is, Kaggle is part of Google, so you have to go through the Google process. All right, so applications of attention in our model. So there are 3 in here. One is in encoder-decoder attention layers. The queries come from the previous decoder layer, and the mandatory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models, such as 3, 2, and 8. So those are citations to other papers. Excuse me. So what we mean by that is, oh, I see. So here we have the queries and the keys. And when you are taking your input sequence, like your language A, and then you're preparing to translate it into language B, you're training Q and K and V for each step separately. But then once you've trained those and you're ready to translate, at that point you use the the Q, the queries are from the previous decoder layer, so the last word that you output in your translation, and the keys and the values come from the encoder layer. So those are trained based on the input that you're trying to translate, again, for machine translation. Okay, so that's how you get relationships between the input and the output. Okay, and this is the sort of thing where I was mentioning, where you'll have like an attention vector, quote unquote, from your encoder that you'll pass to your decoder, and this is sort of doing a similar thing. Okay, that makes sense. And then the encoder contains self-attention layers. In a self-attention layer, all of the keys, values, and queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can append to all positions in the previous layer of the encoder. Okay, so this is during the training of the encoder. So, and that is here. So this is the encoder. So here we are doing attention, and then we pass it forward? That doesn't make sense. Because this is just a feed forward network. This is not a, this doesn't have attention in it. Oh, okay, so this must be at, so this must be something to do with a positional encoding? Double Ride says, is a multi-step optimization question mark? I don't know. The encoder contains self-attention layers. So that makes sense to me because you want to pay attention to the things that you're currently doing. So that would be something like here with thinking machines. You want to make sure that, you know, for thinking is highly weighted, and machines is maybe a little bit lower weighted. So the resulting vector is one we can send along to the feed-forward neural network. In the actual implementation, however, the calculation is done in a matrix form for faster processing. So it's happening within here. Interesting. But it's looking at previous time steps. I think there's something in the positional encoding portion of this model I'm not understanding. All right, let's keep reading and see if that helps it out. Similarly, self and attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve autoregressive properties. So that just means, ooh, excuse me, an apple just jumped off the counter. So that just means that we can't look in the future for our machine translation. We implement this inside a scaled dot product attention by masking out, setting to negative infinities, all values in the input of the softmax, which correspond to illegal connections. Okay, oh, so that's what the masking is. We just ignore everything in the future, basically. So that's good. That's useful. Okay, so this must be unrolled. So we must have this for every time step. So we're looking at step 1, step 2, step 3, step 4, and then for the output embedding, we must be doing the same thing. So this must be a little shorthand. Let's see if it's covered in here. Multi-headed attention. Okay. And then splitting into 8 heads. So this is the thing we were talking about where you train many small models simultaneously. But my question is representing the order of the sequence using positional encoding. Okay, yeah, that is what my question is. And is that discussed further down? Position-wise feed-forward networks. Positional encoding. Let's keep reading and see if this makes more sense. And if it doesn't, we'll backtrack. All right, position-wise feed-forward networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. This consists of 2 linear transformations with a ReLU, rectified linear unit, activation in between. So our feed-forward network X is the max of 0, or X W1 plus B1, so the weights and the bias, times the second set of weights and the second bias. Well, the linear transformations are the same across different positions. They use different parameters from layer to layer. Another way of describing this is as 2 convolutions with kernel size 1. The dimensionality of the input and output is d sub model equals 512, and the inner layer has dimensionality 2048. Okay, so this is just describing that at each position we have a separate feed-forward network, both in the encoder and the decoder, which is fairly standard. I don't think that's super interesting. All right. Innery says, I don't think it's unrolled because why get rid of recurrent nets in the first place? Yeah, that's a good point. I think it's somehow executed in parallel across all time steps. That would make sense. Yes. Yeah, because if you're unrolling it, then it is just recurrent, and I think that certainly the NIPS reviewers would have figured that out. Yeah. I think this positional encoding 3.5 section is going to help answer these questions, hopefully. Yeah. No, I think you're right as well. I think it doesn't unroll. All right, let's keep reading. Hopefully all will become clear. All right. Embeddings and softmax. Similarly to other sequence transduction models, we use learned embeddings to convert the input tokens and output tokens to vectors of dimension D submodel. We also use the usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. That's pretty straightforward. So just you're given your input vocabulary, what word in your input vocabulary is most likely to occur next, except because this is translation, they probably have a separate vocabulary for the input and their output. In our model, we share the same weight matrix between the two embedding layers and the pre-softmax linear transformation. Weight matrix between the two embedding layers and the pre-softmax linear transformation, Symbol 24. Oh, okay, so the vocabulary for both the input and the output must be the same. Otherwise, you wouldn't be able to share a weight matrix between the two embedding layers because that relies on having the same vocabulary. So this must be for something like summarization instead, unless it's a single vocabulary where words from both languages are embedded in the embedding space and some sort of dimension in the embedding space is encoding something like what language it's from. Interesting. I don't think they ever mentioned machine translation, actually. I think that's just sort of the thing that I am most familiar with this model for, so I'm just sort of assuming that that's what they're talking about, but perhaps it isn't. Okay. And then in the embedding layers, we multiply these weights by the square root of D model. So this must be for the same making sure that the gradients aren't too shallow so that you can optimize a little bit more quickly. Or significantly more quickly, I would imagine, since we're taking the square root. All right, positional encoding. So this is what Inri was talking about on Twitch earlier. Since our model contains no recurrence and no convolution, you definitely just said that there was convolution in your feed-forward networks. I think they mean between time steps. In order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. To this end, we add positional encodings to the input embedding at the bottoms of the encoder and decoder stacks. The positional encodings have the same dimension D model as the embeddings, so the two can be summed. There are many choices of positional encodings, learned and fixed. They must mean that there are many choices within learned and many choices within fixed, not that there are many choices and that there are two choices. All right, table 1. This is something we should talk about later, maybe. In this work, we use the sine and cosine functions of different frequencies. So the positional embedding, I'm assuming, of POS, which is the position, 2i equals the sine of the position divided by 10,000 raised to the 2 times dimensional divided by D model power And then the positional embedding for the next one is the next item in the sequence is the cosine of the position divided by 10,000 raised to the 2i divided by d model power. Okay. Sine and cosine functions of different frequencies. Why are they doing this? Because it would seem to me that you could just use like a okay, so maybe the reason that they're doing this, so I'm sorry, I'm just trying to figure out why they're not doing something like they did with the masking, where words at other positions are multiplied by, you know, negative infinity, so that they're zero more or less. Excuse me. So this might be to upweight things that are closer and downweight things that are farther away. So each dimension of the positional encoding corresponds to a sinusoid. Each dimension corresponds to a sinusoid. The wavelengths form a geometric progression from 2 pi to 10,000 times 2 pi. We chose this function because we hypothesized that it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, positional embedding of position plus k can be represented as a linear function of the positional embedding at the position. Okay, I don't understand this math. Bubble Ride says it's like running around a round table. We also experimented with using learned positional embeddings instead and found that the two versions produced nearly identical results. We chose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than ones encountered during training. All right, let's look at this. So so the positional encoding is going to be unique. It's going to be a vector that is unique for every given position, and where position n plus 1 is going to be more similar to position n than position n plus 2. And we know that there's a fixed transformation we can use to get from n to position n plus 1 or position n plus 2. Okay, so we're taking our embeddings and we're adding a positional encoding to get an embedding plus a time signal, and then this results in positional encoding that looks like this. Okay, in the following figure, each row, so this is from again the Illustrated Transformer blog post. Bubble Ride said, if you are at one end, then you are at the beginning. Ryan Chesler says, it performed exactly the same, but we chose to do it anyway because it's cool, the authors. Yes, true. Although I imagine, I mean, if it's something that you can, you know, specify without having to learn, then that should improve training times, right? Okay, positional encoding for 20 words. All right, so word 0, word 20. So up until the 1/2 point of the positional coding dimension, so here we have the sine, here we have the cosine. So the second half is the inverse of the front half. And I suppose the advantage of this is that you can have, you know, many different encoding positions. Formula for positional encoding. You see the code for generating positional encoding. This is not the only possible method for positional encoding. It, however, gives the advantage of being able to scale to unseen lengths of sequences. Okay, well, way to account for the order of words. The transformer adds a vector to each input embedding. These vectors follow a specific pattern that the model learns, which helps it determine the position of each word or the difference between different words in the sequence. The intuition here is that adding these values to the embeddings provide meaningful distances between the embedding vectors once they're projected into the QKV vectors and during dot product attention. So we could have literally just added... Well, okay, no. So the thing that I'm like, why didn't you do that? Is you could just add a number, the vector that is the number of that position. Ryan says, it doesn't even look like they use the full extent of the sine or cosine. Yeah. Bulbright said, if you use sine and cosine, the encoding has no start nor end. Yeah, so I can see benefits to this. It does seem a little more complex than it needs to be, but again, I'm not 100% sure on the math here. Yeah. Yeah. So it does. I do like that things that are closer together are going to be more similar, and going to have a smaller difference between the vectors. That seems useful. You can extend it to sequences that are longer than sequences that you have seen previously because it's a clear progression. Because you know how the pattern is generated, it's pretty easy to get from like given 10, you can figure out what the positional encoding for 0 and 20 are. And then these vectors will be the same for whatever model you're using or whatever. So these aren't learned. You're always going to use the same sort of cosine pattern to encode position. And you are doing this in lieu of something like just using a vector that's like 1, 2, 3. Yeah. I guess this is a way you could do this. Bubba Ride says, using I is kind of complex. Yes. I would agree. So the positional encoding is a specific sequence of vectors based on this sine and cosine set of functions that you add to the embeddings. So your first word is always going to be the embedding for the first word times this vector. Yeah, all right, this is making sense to me. I don't really know why they did it this way, but I guess I trust them. Ryan says, maybe I am misunderstanding the graph though. I'm not sure if I understand the intention of this either. I'm not sure why you couldn't just encode position as an integer with other words as a normal distribution next to them or something like that. I'm still thinking in R and N mode. Yeah, me too. It seems like a clever idea, but I don't know if it's like a good idea. I don't know. This seems like an empirical question, right? Like we can try using other positional encodings and see if they work better. They tried learned ones and those didn't work any better. Shrug. Inri says, why sine cosine for even odd dimensions? Shrug. I have no idea. I have no idea why you wouldn't do just sine or just cosine. Yeah, shrug. I don't know. This might be like a question. This is something that I would have, honestly, if someone just like gave this to me as a presentation, I don't know that I would figure out that this was the thing that was going to be weird to me or not. Well, I understand what it's doing. I don't know why, but let's move on. And maybe I'll see if someone else has written a paper talking about this and what they said. All right, section 4, why self-attention? In this section, we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations, x1 ... xn, to another sequence of equal length, z1 ... zn, with x sub I, z sub I are in the set of dimension d, I guess. Such as a hidden layer in a typical sequence transduction encoder or decoder. Motivating our use of self-attention, we consider 3 desiderata, things that they want. I'm going to need to read this sentence like 4 more times to figure out what they're saying, and I also have to blow my nose again. I will be right back. And I need to make a doctor's appointment probably, because this is getting really annoying. Ryan says, the transformative model did not work well in the insincere challenge, might just not be the best idea for classification tasks. Yeah, I wouldn't use a transformer for classification personally. I would use it more for like style transfer for text, machine translation, probably not summarization, actually, now that I've read about it. Yeah. Bubble says, flu or cold? I think I'm good. Like, I was sick, but I think I've got over it. I think I might be allergic to something. Yeah, hopefully not. Hopefully not. Okay. In this section, we compare various aspects of self-attention layers to the recurrent or convolutional Oh, they're just saying why we're using attention instead of recurrent or convolutional models. That sentence needed quick little copy edit, quick little pare down. All right. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized as measured by the minimum number of sequence operations required. So each layer is going to be less complex, which makes sense because, I mean, we're doing a lot of things here, but it's basically all just taking the dot product or summing, and it doesn't rely heavily on previous time steps. So the third is the path length between long-range dependencies in the network. Learning long-range dependencies is a key challenge in many sequence transduction tasks. This is true. So things like in French, if I was like, oh, look at the sunset, isn't it beautiful? Once I've done with the first sentence, if I want to do the second sentence, I need to know that things like it refer back to the sunset, and then beautiful should be, you know, the correct gender to agree with sunset. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signal have to traverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long-range dependencies. So just the fewer computations you're doing to figure out what's dependent on what, the easier. Hence, we also compare the maximum path length between any 2 input and output position in networks composed of the different layer types. As noted in Table 1, a self-attention layer connects all positions with a consistent number of sequentially executed operation, whereas a recurrent layer requires O sub n sequence sequential operations. So for self-attention, as you increase the number of positions, you do not increase the number of operations. It's constant. So this would be like a hash table, right? No matter how many items are in a hash table, it's constant time to look up something in it. But with recurrent, the more items you add, the more time it takes to do the operations. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d, which is most often the case with sentence representations used by state-of-the-art models and machine translations, such as word piece and byte pair representations. I have no idea what those are. What is a word piece or a byte pair representation? Oh, actually, were there citations here? 31 and 25. Let's scroll on down, take a little peekity poo. Google's neural machine translation system, bridging the gap between human and machine translation, 2016. And then I think it was 26, was it? Outrageously large neural networks. I don't think it was 26. Scroll back up. Excuse me. Byte pair representation, just 25 is what it was. Neural machine translation of rare words with subwords units. Oh my god. Did they invent morphology? Inri says it's a way to tokenize words into subparts. Neural machine translation models typically operate with so this is from Neural Machine Translation of Rare Words and Subword Units by Rico Senrick, Barry Haddow, and Alexandra Birch from Edinburgh. Oh, good school. Typically operate with a fixed vocabulary, but translation is an open vocabulary problem. Previous work addresses the translation of out-of-vocabulary words by backing off to a dictionary. In this paper, we introduce a simpler and more effective approach, making the neural machine translation model capable of open vocabulary translation by encoding rare and unknown words as sequences of subword units. This is based on the intuition that various word classes are translatable via smaller units than words, for instance, names via character copying and transliteration, compounds versus compositional translation, and cognates and loanwords via phonological and morphological transformations. We discuss the suitability of different word segmentation techniques, including simple character n-gram models, and segmentation based on a byte pair encoding compression algorithm, and empirically show that subword models improve over a back-off dictionary baseline for the WMT Wikipedia machine translation task, I think. 15 translation tasks, English to German and English to Russian by up to 1.1 and 1.3 blue, respectively. So we tried it and then we got good results is the point of this paper. Oh, and Inari has shared a link, so let's take a look at that. Simple form of data compression, where the most common pair of consecutive bytes in data is replaced with a byte does not recur within the data. Okay, so this would be like something where if I had a sentence like, Henry and I ate lunch, and Henry and I went to the movies, then we could replace Henry and I with we, which does not occur within the sequence, sort of thing. Okay. Yes, I'm glad that people know that phonology and morphology exist. That's good. Sorry, just like as a linguist, I'm like, yeah, that would help. Yep. Oh my god, it is 10:07. I've been doing this for over an hour. Let's finish this paragraph and then we'll jump back in. To improve computational performance for tasks involving very long sequences, self-attention could be restricted to considering only a neighborhood of size r in the input sequence centered around the respective output position. This would increase the maximum pair length to O of n divided by r. We plan to investigate this approach further in future work. So that seems good, but that also seems like you're going to run into problems with long-range dependencies if you are restricting the words that you're considering at any given time. Yeah, all right, so I'm gonna start wrapping it up now because I actually have a lot of stuff to do, and I peeked at my email before I started this, and it's a lot. Oh, cracking my back. Yeah, thanks for joining me today. I think famous last words. I think we can get through this in one more week. So I think next week is probably going to be the last time that we talk about this particular paper. I would really like to, maybe the next one we'll look at positional encoding, or maybe we'll look at something with images, maybe. I don't know. Bubble Ride says, is there a quick and dirty way to learn linguistics for NLP? There is, actually. NLP, Bender, Emily Bender, there we go, wrote a really great paper that I would highly recommend about 100 things you always wanted to know about linguistics but were afraid to ask. And this is a book, and this must be the book review. So this is, assumes you have some NLP background, assumes you're sort of a computationally savvy person, you know some things about language, but you just you don't know about linguistics. So this is a really good resource that I would recommend. And Emily's great. Really a paragon of the NLP community. Bellride says, post the link, please. I don't think I can post links right now because I'm not signed into the Kaggle YouTube account, but I will, I'll tweet about it. And I am RCTATMAN on Twitter, so you can grab it there. And then morphology is the study of morphemes, which are subverb units. So like in English, if you're making a word plural, you would add a plural morpheme like S to a word. And there's garbage collection outside my house right now, so it's a little bit clunky. Yeah, so thanks for joining me, guys. I hope this was informational. I'm definitely getting a better sense of transformers. I still don't know why we're doing this way, but yeah, it's an empirical question. And I will talk to you guys on Friday for live coding, and next Wednesday when we'll finish up this paper. All right, thanks for joining me, and if I don't see you before the new year, Happy New Year. Bye.